I'm Francisco Blas Izquierdo Herrera. I come from Spain. He is Leonid. He comes from Sweden. He's going to be my assistant. You will soon understand what that means. And I'm going to speak about Gentoo Hardened. As a side note, please feel free to interrupt me at any moment. And during the questions and answer session at the end of the talk, if anybody has a question, he can try to ask over Twitter or on our IRC channel. And if I manage to read it, I will answer it. That goes for the people on the streams, okay? So, as I was saying, I'm going to explain how Gentoo Hardened works. And yeah, that sounds a bit stupid. I'm going to explain how some attack vectors work, and then how we prevent them from being effective in Gentoo Hardened. So you can try to understand the inner workings of it. So what's Gentoo Hardened? Well, blah, 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 blah. Raise hands who doesn't know what's Gentoo Hardened. Oh, you guys have mistook your room. I think you should go over there. And no, Gentoo Hardened is basically a Gentoo distribution which has been modified to make it harder to exploit. So what that means is that since it's harder to exploit, for example, the last bug regarding proc-pit mem is not as easily exploitable in Gentoo Hardened as it is in, for example, Debian, just to pick a random distribution. Why is not part of Gentoo itself? Yeah, that's good, but, well, let me use one word, risers. Gentoo users tend to be like risers. They want to get this 0.0001% of extra performance they can get with oh my god, optimize when they compile their own package. Yeah, since most of these features usually mean we are going to have small performance impacts, we are going to have to slow down, and we cannot get all of that inside Gentoo. But a lot of work is being done nowadays to get some of these features integrated in Gentoo itself. For example, 40 sources is already available. We are working on getting Pi available, if I'm not mistaken. And I think efforts towards SCP will be retaken back then. So, wow, we have a small Gentoo user over there. Let's explain what's a Stack Overflow. That's quite easy. Here, my assistant is going to beat the program and is going to show you what he does. Okay? Perfect. So, we are going to call a function. So, first, insert your arguments, please. Okay. Now, we are going to call the function itself. So, please insert the return address. Okay. Now we are going to add the frame pointer and the local variables. Please do so. That's all. That's a function call. Then we want to go back, so please remove the frame pointer. Note the return address, so you can go back to the function and the arguments. Yeah, exactly like that. Let's go for the classic overflow. We have his stack like here. So we are going to put some trash on the local variables. Then we are going to put some trash on the frame pointer. And we are going to put an address in the NOP sled as the return address. That's upwards, please. Yeah, exactly. Because in x86, the stack grows downwards, but buffers are accessed upwards. So we now put a lot of knobs. Go up. And we now put our cell code. And then we are going to do the return. Okay, go back to the... So we remove the local variables. We remove the frame pointer, yeah. Now we look which address. We are going to go back to somewhere around here. Yeah. And he keeps executing from there. And we execute the code we want. There is another kind of attack. It's called return to libc. So, function again, perfect. So we put some trash in local variables and frame pointer. Here we are going to put the function address we want to call. We are going to push a fake return address here and some arguments we want to get, okay? So we first remove the frame pointer, perfect. Now you see which function we are going to call. Yeah, it's system, cool. So now we access the arguments we have put in here, and we call system, I don't know, rm-rf/. So that's basically a Stack Overflow. What do we need to do that? Well, for the classic attack, an executable stack is needed. The stack address is also needed, so we can know where we have to return to, and we have to access to that return address to be able to modify it. With return to libc, all we need is the function address and the address we want to return to. Okay, so now we go with SSP. What happens now? We have inserted here a canary. What's a canary? Yeah, exactly. It's a bird. Everybody knows people in coal mines went with canaries, and when the canary dies, you are fucked. Because it means, yeah, it means there is grisou in the mine, and it's not good for you. You have to run as fast as you can and hope for the best. So, since we have the canary, we are going to do this any of the attacks. We want to modify the return address, and we change the value inside the canary. So when we are going to return, before returning, our example is going to, well, is going to check the canary, and we'll say, yeah, it's dead, it's not the same. Nah. So we cannot access easily the frame pointer and the return address anymore. Of course, if we guess the value of the canary, yes, we can still access it, but no, it's like 32 or 64 bits harder. What happens with pie and pig? That's not pictures of pies, in case you are wondering. It basically means making our code independent of position, so we can put it wherever we want. So our dear example here is going to show it with a classical example. A normal program will just execute here. Yeah. But since now I'm the kernel, I'm going to tell you, since you are pig, go over there. And you see, we are executing the code there instead of here, which means that in order to know where we want to return to, it's going to get harder for us. Exactly. Exactly. Since he is not there, the return won't work well. Another thing we have is for diffuse source as well. This is quite easy. Basically, when we are compiling, we are going to check some things we know they are bad. For example, who uses still the gets function? Yeah, I see lots of hands raised. Ooh, yeah, you shouldn't use get. So, well, it basically checks statically as many buffers as it can in order to prevent overflows. In case they detect some of them, it's going to say, okay, there is an overflow here. I'm going to compile this, but you are on your own. If the overflow eventually happens, the program is going to die, because it adds some checks and some words. So when the overflow is going to happen, it calls abort and kills the application. So ASLR, we go back into the kernel. Well, ASLR and rand mmap basically is like taking my friend over there and putting his head down, then his legs up, etc. We are going to change the completely the mapping. So the code is going to be in a different place, thanks to us as SLR, and thanks to rand mmap, the stack and the heap, etc. are going to be in completely different places. Well, you can try to just do it, but yeah, okay. No, we are going to go with random stack. It's exactly the same with the kernel stack. For those of you not knowing, there is a stack in the kernel too. It's time you go to a syscall. And if we make the address random, we make accessing this stack harder. What happens with not executable memory? Yeah, well, come here, Leonard. Here we are going to have our standard program that is going to try to execute code in the middle of the stack. Please go ahead. Yeah? Yeah. Now we are going to mark the stack as not executable, and you are going to try to execute the code. Exactly. It doesn't work. Why? Because he is going to read the code and no, we cannot do that. Yeah, like trying to read the Spanish. We have also in protect restrictions. What we do here is enforcing these memory protections we have added. These are the big friend of big code writers. Yeah, Java really loves protect because it's going to try to make readable, writable, executable mappings, which means it can be able to read that spot of memory, it can write in it, and it can execute it all at the same time. That's not good, because if you have a chunk like that, all you need to know is where it is, and you are going to be able to execute anything in there, in case we have any kind of overflow. What we do here is enforce that you can only have read and write or read and exec, but not read, write, exec. Of course, this can be disabled on a per binary basis in case a binary needs it. That's the case of Skype, yep, of Java, and a few others. Then we also remove addresses on SMAPs, maps, stat, and a lot of places in barproc. Well, what this means is that we are going to make it a bit harder for an attacker to get information about where the stack and the libraries are in order he cannot try to make a privilege escalation. We also are going to restrict barproc only to a user. I mean, which this means is that in order to access barproc bar PID, you need to be the owner of that process. Otherwise, you cannot do that. Of course, there is a wicked restriction that can be put when you make your kernel, which allows you to add a group that can access these addresses in barproc bar PID, but usually it's not needed. So yep. No brute force deterrence. That's a good one. Here our friend is going to show us with a simple example how it works. So, no, try to fall. Nah, try to, I don't know, execute an invalid instruction. Then drop dead. Yeah, like that. So, when I try to execute an invalid instruction, I'm going to beat the parent, he's going to beat the son process. So, I execute you. Yeah. So, the process dies, and now I want to execute him, but until 30 seconds have passed, I'm not going to be able to do so, since I won't be allowed to fork. What this prevents is that forking daemons, like Apache, for example, can leak information easily. So, let's go for railroad and bind now. These are some modifications in the toolchain. Basically, we mark as read-only and some important sections like the global offset table. So, well, we are going to explain what's a global offset table. My friend over here is a global variable. I'm going to be the code. I'm pointing to where the global variable is. So, when I want to access the global variable, I'm going to say, oh, it's pointing here. What happens if an attacker modifies that and, I don't know, points to him? Well, then we are going to try to read the global variable and, yes, it means that you are authentified. Cool. The PLT is exactly the same, but instead of pointing to global variables, it's pointing to routines that come from libraries, okay? So what we do is just make the program with bind now, load all the libraries it needs once it starts, and since it loads all the libraries then, we mark all these tables as read-only so they cannot be modified afterwards. It's not quite hard, and it usually just means a small impact performance once you start the application, but nothing else. So is there anybody here that is a developer of any distribution not being Gentoo? Cool. Please, try to do that in your distributions if you don't. It doesn't take that much. No, we are going to go for race conditions. So, our friend over here is going to be a program. He wants to broadcast a message to all of you. Please, go ahead. Yeah. Okay, so no, you are going to try to do the same, and I'm going to be an attacker, okay? Yeah. No, here's not an IP address. You are going to just connect to my server because I'm evil. So, well, that's how a race condition works, basically. We have a program that gets before the program we want to get there and does the evil things. We can prevent that with some restrictions on linking and FIFOs. Basically, so you get an idea, we are not allowing FIFOs and hard on bar TMP, and hard links are a bit harder to make. So basically what we do is that if you want to have a FIFO, you can, but please do so in a directory you only own. So that way, at least you know that only processes that have the same group of you as you can access that FIFO, not anybody. Okay, let's go for user space dereferencing. What this means, it's basically that we go, here's going to be the kernel now, and I'm going to be the bat program, okay? In normal conditions, I'm going to call something pointing to null. And yeah, it's going to point over there because I'm not going to have anything mapped there. And you are going to file and say, well, no. Exactly. You cannot do that. Then we will get an oops, and well, and the kernel dies, and we have to reboot the machine. Now we go for the evil program. I first tell the kernel, please, map some code here. And now I call the function, and he has to execute now, null. Oh yeah, you can execute it. So that's how null address space dereferencing works. We are going to explain now how to prevent it. First way we have is using the ref. There are various ways in which this works, but it can be summarized up in we are not going to allow normal kernel functions to access address space. So we are going to do the example now. Please, mark something here. Yes, you can. Yes. No, try to execute it. Exactly. That is how it works. Now we go for the kernel exec Gcc plugin. It's basically a small UDRef. It's quite easy. We just set the first bit of the function pointers to 1, so we make sure they are always going to point to kernel space. Then we also have the mine and map address. So yeah, I'm the bad program. Please map some code here. No, you can't. Yeah, and let's go now for what's an info leak. For that, it's going to be helpful if I can get a piece of paper. Cool. So, we have now a copy of, oh, it's FOSDEM. So let's suppose I want to access this bulk over here. I want to know which one is it, but I'm not supposed to be able to access the next one, okay? So, please, read me one talk. So, compiling Smalltalk to fast native code. Okay, that's a space for one talk. Please, fill this space with 2 talks. So we have no filled 2 talks in the space we had, but we only should be able to access 1. That's because maybe we passed a big buffer or a big size. This happens at times. So basically what we do is obtain kernel information. Maybe here, instead of the second talk, we could have the, I don't know, the key for the full disk encryption we have in my system. That could not be good at all. What's data rewriting? It's approximately the same. Let's suppose I want to write one of the talks. I'm going to say, no, this one is now going to be marshmallows and unicorns. But I'm going to use a function that has a small bug and is not properly checking boundaries. So, marshmallows and unicorns, and please fill in the, I don't know, I'm a bad guy, I'm going to be rude. So, now when he returns to me, he's overriding something he shouldn't have to, and I could be rude, for example, because he wrote, yeah, I'm going to be rude. So, how can we prevent it? Well, we have a protection called reference counter overflow protection. It works in a simple way. I'm going to point it to that object, okay? So, okay, reference it once more, okay? 2. Reference it once more, 3. Once more, 4. Once more, 5. Once more, 0. That's the overflow. So if we check that in case we are at 5, we have an object we cannot reference anymore and we cannot deallocate, it's going to be reference it 1, 2, 3, 4, 5, 5, 5, 5, 5. The reference it. Oh no, we can't. It's 5, 5, 5. It stays at that. What this does is converting an issue, which could be make an object be deallocated and then allocated again with other reference, so we could overwrite it. It becomes just a memory leak, which is bad, but it's not as bad, obviously. So, we are also limit comparisons on user copy. Well, that's the example I have shown before. If we have a buffer that is longer than the address we are going to write to, well, then we are fucked because we are going to write what is after the buffer. What we do is just say until here, and for each function we are going to check that the size is the correct one. It's a lot of handwork, and well, it's approximately like, I think, 90% of the PAX patch. So, yeah. Well, then we also have the Constipate Gcc Plugin. This works in a similar manner to read-only memory. What we do is that things like, for example, function pointers that are known at runtime are going to be read-only. Why? Because in most cases, what the kernel does to have a family of sockets is have an struct that has the methods that have to be called for each socket, for example, or for each file system. So, he's going to be the kernel, I'm going to be the struct, just so you get the idea. You just try, I don't know, to send a message. Yeah, okay, you have to use this function over here. Yeah, no, you need to use this one. And so on, okay? I'm the struct, he just checks which function he has to use. What happens if somebody manages to write that function to, I don't know, maybe make root the process that called you, okay? So, yeah, use this function, it means I'm going to be root. Yes. This other. Yeah, so as you have seen, if we write the addresses, we can manage to change the behavior, which is bad, obviously. In this case, since I'm going to be constant in case anybody tries to write something, he's not going to be allowed because I'm going to be on read-only memory. Let's go for memory sanitization. It basically erases the pages that as soon as they are freed. What this means is that we reduce the live data is in memory. The shorter the time the data is in memory, the harder it is to get anything from there. So, well, I'm going to die, and in normal conditions, he won't allocate me, but in this case, he's going to say, okay, I'm going to fill you with zeros, and then I disappear. Yeah, that's how memory sanitization works. Kernel stack sanitization is the same thing, but we do that with the kernel stack before returning from any syscall. The stack leak is a GCC plugin that tries to improve that just by setting some limits, so you can know approximately how deep the stack is going to go. And then we go to another kind of attack, information compilation. Please, all of you that are in sync, you are having fun with your laptops. If you don't mind, please try writing DMESG, then press enter in the terminal. And you will see that I can see, for example, which modules you have loaded. I can see which hardware do you have. I can see also a lot of socket types you have. So, oh, maybe I can even see the version of the kernel you have. That's really nice. I really like to know that you are still using a vulnerable kernel. Yep. So, first thing we do is that normal users cannot use the mesh, so they cannot get any of this information. We also hide the kernel symbols, which means that only processes that have access to that information explicitly given can know which symbols, which means which functions and which global variables we have in the kernel. We also try to hide the kernel processes. So, for example, the process that is executing the disk encryption cannot be seen by normal users. That is with GRSEC. We also have some additional restrictions, so you cannot see information like, for example, what's on the memory manager. And you cannot try to derive any address from that information. And we also restrict access to sysfs and debugfs to non-root users. Please don't do that if you have a desktop. If you do, you are going to have a lot of fun when you see a lot of applications not working, and you are going to come to the channel and ask us, hey, this application is not working, please do something. And we are going to have to just tell you, please disable this restriction when you compile your kernel. Yeah. And we also deny ptrace on non-readable SUID and SGD binaries. Why? Well, in normal conditions, if I ptrace a process like this one, when the kernel executes it, even if it's SUID, it's going to make it a normal under my own user. So now I can use ptrace to see, oh, it has a head here, and it's this model of head, so these are the symbols we have. He has the local variables here, is this kind of local variables, etc. What we do is that since in Gentoo, SUID processes, SUID binaries cannot be read by normal users, in case that's the case, I'm not going to be able to check if he has a head, because I'm going to tell the kernel, hey, please, oh kernel, that you thought that you are in heaven, come and tell me, where is the head of this process? And he's going to tell me, you cannot know. You don't have read access to this process binary. Yeah, it's quite simple. Then we have the kernel rootkits. Yep. Ask the question, I will repeat it. No, because root will still be able to read it. So it's not a problem for a rootkit detector. What we do is that normal users cannot read them. Yeah. And even if that weren't the case, well, in normal conditions, the user access control works like that. It's root. Okay, we don't care about permissions. What? Redur? Sudo. Yes, you will need it in order to to know, I'm going to show it. This is a Gentoo Hardened system. Okay, that was not supposed to be like that. Okay, so Control Alt what? Oh, okay. That's enough. Wait. No, in my case it's used to, but maybe it's in user scheme. No. Okay, yeah. Yeah. So if you see here, we don't have read permissions for normal users. Okay, that's true, but for sudo would be the same. So if I try to see what's inside, yeah. No, unless he has read permission. If you want sudoers to be able to do that, you just set the group here to sudoers and add a read bit here, and yes, he can do that, but in normal conditions, he cannot use ptrace. Okay? Okay, so that's let's go for kernel rootkits. What's a kernel rootkit? Okay, this is my friend here. He's going to be the kernel now. Yeah, this guy that is over there somewhere. And I'm going to be a bad guy. And oh yeah, here you have the function with which you write. Okay. And before you write, please send me an email with all the information you have here. I'm going to just make it a bit bigger and put this information here. And okay, right. Okay. And yeah. Oh, okay. Your password is PASSWORD. Oh, it's password. I got it. Yeah, that's a rootkit, basically, a kernel rootkit. It can be improved as much as you can. It's just a simple example. So first thing we do, we are not going to allow random writes on memory. Okay? Bardep, barmem, bardep, barkamem, that's all. Nobody wants to use it, believe me. Why? Because they can be used to insert code into kernel space. You can just go to the physical address where the kernel is and say, okay, here you have the function to read, let's modify that. We also disable privileged I/O. Please, desktop users, don't do that. You are not going to be able to run Xorg if you do. But in normal conditions, yes, there are some system calls that can be used to access directly to I/O devices. So for example, on a server, we don't need to do that at all. So we can just enable it. And well, let's go for other attacks. We have seen some reasonable standard attacks, but there are a lot of creative ones. So we are going to see how we can protect against them. First thing, the BM86 mode, it's obsolete. Almost nobody uses it. And you can disable it completely on x86 kernels. You don't need to do that on AMD 64 kernels because it's not there. It's not allowed by the ISA. We also have hardened module auto-loading, so you cannot try to make the kernel automatically load bugging modules when you request for features that it doesn't have. You have to do mod pro and be a root user in order to do that. We have siege root jail restrictions. Please hands up people that has ever used BSD. Yeah, you know what's a jail, don't you? It basically is like a siege root, but you cannot get out of it. Yes, so we provide a kernel enhancement that makes siege roots work like jails. Because, for example, on a server, the main reason why you want to do a CH root is to enclose a process. And, well, yeah, Pipax managed to move the thread info outside of the stack. And you're going to tell me, oh, what's that? We don't care. Okay. Here's going to be the kernel. Please have a random stack. This is the stack. It goes down. This is the thread info. here we have information like which is the user ID of the process. So I'm going to manage to do this. Filter stack, 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 and note that I'm here, I'm going to write 0, and I'm going to be root. Then I go back, and I'm root. Yeah, so to prevent this kind of vulnerabilities, it has been removed. So I think now we just have a pointer pointing to the place where the thread info really is. So you cannot set any arbitrary value, but you can try to make it point to a kernel object which you don't know where it is. We also have a consistent multi-threaded privilege enforcement that's rather new. Just so you get an idea, other C libraries, not glibc fortunately, don't set the user ID and the capabilities and so on of all the threads of the process after calling CHUID to change the owner of the process. So, well, what we prevent here is that in that case, you can try to force other threads to execute things it shouldn't, because all of them will go with the new dependencies automatically. We also have the Overflow Gcc Plugin. Well, what this basically does is that if we have a size counter here, we are going to make sure that if we have this size counter plus this other size counter goes outside of limits, okay? Yeah, because otherwise, since the limit is going to be this one, it could go to 0 and the new size maybe be minus 25. It's hard to make that size to go back. We also have active kernel exploit response. What it means, well, basically when you have an oops, for example, in your kernel, the kernel is going to ask you to press enter and we'll try to continue. If we know who caused that oops, we are going to ban him from the system. And I think in the latest version it means all your processes are going to be killed and you are not going to be able to do anything with that user during 15 minutes. Which makes exploit using a bit harder. We detect oops and another bad conditions like UDREF violations and so on. But, well, and of course, if the process is root, we just kill the machine and go down. It's better than having an exploit after all. We also disallow code execution on non-trusted folders. That's really hit H, a really big hit H. Basically, you can set a set of users that is not going to be able to create their own binaries and try to execute them because they are going to be able to only execute binaries owned by root, which usually means binaries that the system administrator trusts. And there is an extended version which also tries to prevent some kind of racist conditions, preventing you from executing code. It prevents other users from executing code on directories they don't own or are owned by root, and that must be non-readable by world. So you cannot just remove the binary and then change it. We also have ptrace deterrence over non-children processes. Here, I'm going to be the bad guy, okay? And he is going to be a children process or a process. And I'm going to ask the kernel for something, okay? So, if we don't have this thing over here, since he is not my seal, I just ask, hey, I want to access this information over here. It's the key, it's my GPG private key. Yes, please, give me it. Yeah. In our case, I'm going to ask the kernel to ptrace the process in order to access that information, and he's going to tell me, you shall not. And I'm not going to be allowed because he's not my children. Of course, in normal conditions, like for example, when we use GDB, I used spawn, a Leonet over here, and tell the kernel, which is now my children, hey, please, I need to ptrace that in order to debug it. And he's going to tell me, yeah, you are the parent of this process, you can do that. Okay? Yeah. We also have a process number enforcement on exec. Anybody of you know what's a fork pump? Yeah, everybody has tried to exploit a fork bomb. Let me explain how the exploit works first, okay? So I'm going to be bad user, the system administrator that controls me because he knows that I'm a really bad user. Is going to limit my number of processes to 100. Well, it's going to limit it to 2, just for explanation purposes. So I fork. Yeah, we have 2 processes now. I try to fork again, and no, you cannot because your limit of processes is 2, and 1 and 2. No. But what happens if I now make him execute su? So now he's owned by root, and I say, hey, can I fork? Yes, you only have 1 process. Quick! And we get another process. I make this one execute su. Oh, can I fork? Yes. I make this one execute su. Can I fork? Yes. And so on. So what we do is that this process number check is enforced also when you try to execute any process. So you are not allowed to do XX when you have hit your limit in process number. We also have a Tcp Udp Black Hole, blah, 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 blah. This basically works like follows. If we don't know what to do with a packet, we receive it. Instead of following the standards, we are going to do nothing. It's like some sort of, yeah, exactly, government agency. Yeah, it's like some sort of micro firewall. The good thing is that if we do that, we don't have sockets in the last AC key state waiting for the AC key coming from the process after a fin, which can be exploited to get to consume all the sockets inside a system. Well, we are not going to have the sockets waiting for the last AC key because we know that in case we get it, we are going to do the proper thing, nothing. Yeah. And we also have some protections after the attack. That's the last, well, almost the last part of the talk. Yep. So we have socket restrictions. We can have a set of users that is not going to be able to create a new client, server, or any kind of sockets. It's very useful if you, for example, have I don't know, a web server user, which you don't want to be able to create a client sockets to access the internet. We also have a lot of kernel auditing features. We can, for example, know every exec that a user has done. We can know every sachdir a user has done. We can know when change has, when the date has been changed, and a lot of things. We also have currently it's 3 sets of MACs, mandatory access controls. We first have the Linux mandatory access control, which is Swift over here. Yeah, there he is. He is the one that writes most of the policies for Linux. We then have RSBAC that comes with YERSIC. It's the best, but it's the harder to handle. And we have a new mandatory access control system called RSBAC. Well, let's call it resurrected, because yeah, it was removed from the project because nobody maintained it. Then somebody stepped like 1 year after we removed it and say, I'm going to maintain it. So yeah, it's resurrected. The documentation is not updated still. So if we'd like that if you want to experiment, you use it and report us your issues, but don't use it on critical systems, please. Not yet. We also have runtime read-only mode protection. That's similar to what we have in BSD, okay? So this works like follows. This is going to be a mount point, okay? So I'm going to manage, I'm going to be a bad root user. I manage to hack into the system, okay? And I will just tell the kernel, please mount it like read-write. Yes, it's the example. And note that it's read-write, I modify it and mount it as read-only and nothing has happened. What we can do is that when we enable this feature, new mounts and remounts of read-only partitions as read-write are not going to be allowed. So, please, kernel, we want you to mount this partition over here. I am going to overwrite as read write. No, not allowed. Oh, okay. That's the most part of the talk. I'm going to speak now about the future about Gentoo Hardened. So the people that is not the 2, 3, 4 developers of other distros might not be interested in this part. Okay. Well, everybody knows that Gentoo Hardened is hellish, infernal. It's the worst thing that can happen to you. It's a nightmare come true. Well, I could start also collecting feedback from fellow Gentoo developers. I'm sure Scarabeus over there will say, yeah, it's the worst thing it can happen when a packet files on Gentoo Hardened. I'm alone, nobody wants me. Yeah. There are a lot of cases of frustration after not being able to make the system run or install it at all. Well, most of our efforts now are trying to improve that because, yeah, being secure is cool, but being usable, it's even better because then you make the others secure too. And, well, we think we can do that, and we are working currently towards that objective. And, well, some steps we are taking. First one, we try to improve our current documentation. So, if you cannot understand anything in our documents, please open a bug. It means it's not good enough. And it means I, as the main documentator, have to rewrite it. So, yeah, if you are bored enough and you can get your grannies to read the documentation, we'll appreciate it. It's a good feedback. Yeah. We also have refocused the community. If you go now into the Gentoo Hardened channel, nobody is going to tell you to read the fucking manual. Well, indeed, that has changed a bit. Instead of saying you read the fucking manual, I'm going to tell you, here is the manual, the information you're looking for is here. If you have doubts after reading it, please come back and ask. It's way better than just read the fucking manual. At least it's useful. And yeah, we also have managed to make most of the community members aware that they were newbies once ago. That sounds stupid, but it's the best way we have to prevent read the fucking manuals. Because if a newbie comes by, you don't see a newbie there. You see somebody, oh, I see a young me here. And yeah, another young me here. Yeah, it changes a lot the empathy you have in somebody. We also have to take some time explaining in books. What this means is that if you open a book because something doesn't work, we try to just mark it as invalid and forget about it. We are going to try to explain you why it's happening and send you a link to the document that explains how to fix it. Okay? We also have expanded now, aside from the IRC and the mailing lists, which, let's get realist, almost nobody knows how to use. We also have Twitter and Identica. So lately we have been receiving some doubts over Twitter and Identica, and we try to solve them. Well, we also have better predefined kernel default profiles. Please, everybody, welcome the new virtualization profile, which means is that most of these features I have been explaining before can be set automatically just choosing the profile, so you forget about everything. We also have Linux policies up to date. Please, a big round of applause for Swift, who has done a lot of work. Please, no, I'm really meaning it. Because he has done a lot of work making the kernel policies, the default kernel policies in Linux up to date, and we still have a lot of work to do. And well, we have a lot of new features like repdep packs, markings for the application based on extended attributes instead of writing the application code, etc., which fix a lot of known issues. For example, anybody knows what's Gallium? Yeah, I see some hands. It's the new graphics driver stack for some drivers like ATI or Intel. Yeah, it's for 3D and so on. It has a cool feature. It compiles the kernels, the shaders as big code. As big code, no, as JIT code. So yeah, that's not very good. because it's a library, so we cannot just mark the binary to say, hey, you need protect restrictions. What we have done is develop a tool that allows you to mark the library and then propagates the restrictions over the rest of the binaries. It means, yes, it's less safe, but it's more user-friendly, and it solves the issue. Or, for example, the exact based markings. Anybody has ever used Skype? Hands up. Yeah, I'm going to tell you something. I'm going to tell it without the microphone because I don't want this recorded, if you don't mind. Yeah. So going back to the topic, it has Skype has a lot of cool features, like it self-checks the binary to make sure you have not tampered with it. So you cannot mark the binary, because if you do, then it fails. Yes, that was my face the first time I discovered that. Yeah, so that's why we have other things like extended attribute based markings, so you don't modify the binary and you can use it. 5 minutes left, perfect. And well, that's all. Now it's time for questions and answers. These slides will be made available to FOSDEM organizations, so they will provide a link for you to them. No need to copy it. And if you don't manage to get them, just come to me on the Gentoo Hardened IRC channel. I'm Klondike, or write to @clone in Twitter or @cloned in Identica, and I will just send a link for them to you. So, questions? And Janet, pick the microphone and go to the people having questions. I will meanwhile try to open that. Go ahead.
Hello.
Hello.
Thank you for your presentation. I would have to say, have you have some experience in hardening the kernel namespace?
The kernel namespace.
For example, Linux containers, LXC,
Yeah.
OpenVZ.
Yeah. Well,
have you some experience in that?
Yes. It's a pain in the ass. Because basically what you have is a patched kernel which touches most of the kernel and want to patch with another patch that touches most of the kernel. There are some patches, I think, for Linux containers available, but they are quite old. So yeah, usually if you want to use the isolate process, I recommend you use chroot based jails and put the process in a group that has no access to sockets. That should do most of the isolation you want. Okay? Any other questions? No? Oh yeah. Hello. Handle me the mic, Leonid. Okay, ask the question. I will repeat it for the people streaming. Okay, yes. He asked me about Gentoo Hardened profile in Select. Well, indeed, it's not one. I think it's like, if you are using HMD64, it gets up to 4, because we have the Linux profile, the Linux no multi-leaf profile, and the no multi-leaf profile. Basically, what it sets is it sets up the hardened use flag. It masks packages that are known to cause issues, so you are warned before you try to emerge them. And I think that's mostly everything. I mean, there are a few. Oh yeah, sorry. Huh? use flag? Yeah, it says the hardened use flags. I think currently they are Pax kernel, hardened, and I'm not sure if we have any other more. I think no. Yeah, so that's mostly what it does. My recommendation, if you want to have an easy Gentoo hardened system, just set the profile. It will ease a lot of things because you will notice issues before they happen. Yes. Yeah, basically you use select a profile, okay, select a new profile, compile the system with emerge -1 system, then re-emerge world, and once you have re-emerged world, you are hardened. Welcome aboard. Not more hard than that. Any other questions? I heard you have one. Okay. He's asking if we have certification for Gentoo Hardened, summarizing it very much because some company wants that certification. And, well, no, we don't. Why? It costs a lot of money, and I'm not sure if we can combine the Gentoo Foundation to do that. Yeah, that too. It's also very hard to certify a rolling distro, as Peter just said. But if you want to sell Gentoo Hardened to the enterprise, I'm going to tell you how you can do it. You don't have to go like, okay, we have this certification. Just show them a link to CVE 2012-0056, which is a local root exploit, and show him how he cannot exploit any of those exploits for that CVE in Gentoo Hardened. And then you pick a certified distro and show how you can exploit it. Okay. Yep. Right now, it's another part that is left to the system admin. Well, sorry, let me repeat it. And that's the last question, so we go outside and ask any other questions. He asked if exploits happening in user space, like cross-site request forgeries, are handled by Gentoo Hardened systems. No, currently that's not the case. But if anybody wants to step up and make it happen, we'll have a lot of friendly people trying to do its best to get it inside, because it's a really good thing. That, yeah. Well, regarding GLSA check, the security team is a bit not up to date currently. They are making their best efforts to fix that. But yes, I think we should try to improve that, and we are going to end here. Thank you very much.